Hello everyone. So in last lecture we have studied about force. So force on a charged moving particle was magnetic force was Q into V cross B, and force on a current carrying conductor was I into L cross B. L was the displacement vector and direction was from initial to final point, and force per unit length for parallel current carrying conductors was mu naught upon 4 pi 2 I1 I2 upon distance between those wires. So suppose if current is in same direction, then force will be attractive. If current is in opposite direction, then force will be repulsive in nature. Now we will study about magnetic dipole. Then we will write the equation for torque on a magnetic dipole and work rotating to the magnetic dipole, then potential energy. In the end we will see atomic magnetism. So suppose there is a loop in which current I is flowing. If area of this loop is A, number of turns is N, then magnetic dipole, which is represented by M, will be N into I into A. Remember this formula. And M is a vector quantity, axial vector. So direction of M will be along the axis of this loop. So it can be outside of the paper or inside of the paper. Now how we will decide the direction? So for direction of M, if you curl your fingers in direction of current, then your thumb will be in direction of M. So if we curl our finger in for this loop in direction of current, then M will be outside the paper. So here direction of M will be outside the paper, and for this loop M will be inside the paper. Now we will write the torque on a current loop in a magnetic field. Suppose this is a loop and there is a magnetic field, uniform magnetic field, then torque on this loop will be tau equals to M cross B, or we can write M into B sin theta. Theta is angle between M and B. So this equation tau equals to M cross B can be written like this, MB sin theta, or M can be written N into I into A B sin theta. Now if theta is 0 degree, then torque will be 0. Theta is 0 degree, that means angle between M and B is 0, right? So over we can say plane of loop is perpendicular to B, right? If suppose this is the theta is 0 degree, or we can say theta is 180 degree, sin theta will be 0 degree, that means tau torque is 0 degree. Suppose this is the our loop, so direction, and suppose this is the direction of magnetic field, so here the M will be in direction of outside the paper. So here we can see angle is 180 degree. Over magnetic field was outside the paper, then angle will be 0 degree here, right? So if the plane of the loop is perpendicular to the magnetic field, then torque will be 0, right? Now when will be the torque will maximum? So torque will maximum when theta is 90 degree. It will be n into I into A into B. It will be when theta is 90 degree. What is the meaning of 90 degree? So 90 degree it will be when loop, our loop, plane of the loop is in magnetic field. Like here, magnetic field direction is in this direction and this loop lies in this magnetic field, right? So the direction of M will be here outside the paper, and the direction of magnetic field is here in this direction, so angle will be 90 degree here. So torque will be maximum in this condition. Now we will see work done in rotating a magnetic dipole. If we rotate the magnetic dipole by a small angle d theta, then work done will be integration of tau d theta over, if we integrate this from theta 1 to theta 2, so this will be mb sin theta d theta from theta 1 theta 2. Integration of sin theta is minus cos theta, so work done will be m into b minus cos theta, or we can write cos theta 1 minus cos theta 2, right? So this will be the work done. If we write potential energy of magnetic dipole, so potential energy of magnetic dipole will be minus m dot b. So actually potential energy of a dipole is defined as work done in rotating the dipole from theta equals to 90 degree to a given theta, right? So this can be written like this, minus mb cos theta, and work done will be change in energy. So from a theta 1 to theta 2, it will be u final minus u initial, so it will be minus mb cos theta 2 minus mb cos theta 1 if we are rotating from theta 1 to theta 2, and this becomes mb cos theta 1 minus cos theta 2, and ये इक्वेशन हमने फोर्स की टाउ डी थीटा के इंटीग्रेशन से मिली थी. So here you have to remember, first of all, m equals to n into I into A. Second, torque was m cross B, and the work done is delta U, and work done can be work done is delta U, and U is minus m dot B. Now we will solve a question. So find the magnitude of magnetic dipole of the current carrying loop A, B, C, D, E, F, A. Each side of the loop is 10 cm long and current in the loop is 2 ampere. So I is given 2 ampere, side is given 10 cm, that means 0.1 meter. Each side is 10 cm, that means this is a square. So this will be a square and this will be also a square. So area of this will be a square, that means 0.1 का square, that becomes 10 raised to power minus 2 meter square. Right, now what we will do in this types question, we will assume a side here in which current is flowing in this direction. Similarly, we will assume another side in which current is flowing in this direction. So total current will be 0 here. Now if we check in this loop, if we write magnetic dipole for A, B, E, F, A, this loop, then suppose this is M1. So this will be with direction, this will be number of turns not given, that means number of turns is 1. So M equals to N into I equals to 2, A, area is 10 raised to power minus 2. Now curl your finger in direction of current, then the thumb will represent the direction of M. Suppose this is X direction, this is Y direction, and this is Z direction. So this loop is in X, Z direction. So if you curl your fingers, then thumb will represent the minus Y direction. Similarly, write the equation of M for B, C, D, E, B loop. M2 will be number of turns is 1, I is 2, area is 10 raised to power minus 2. Now curl your finger in the direction of current, then thumb will represent the direction of M. So this loop is lying in the XY axis. So if you curl your finger in direction of current, then your thumb will be inside the paper. That means it will represent minus K cap direction. That means total M, total magnetic dipole will be 2 into 10 raised to power minus 2 minus J cap minus K cap. If you want to find the magnitude, then it will be 2 into 10 raised to power minus 2 square root of minus 1 square plus minus 1 square. It will be 2 root 2 into 10 raised to power minus 2 ampere meter square. Now in next question, it is given a circular coil of 100 turns. So number of turns are given 100, radius is 0.05. मैं थोड़ा सा फास्ट जा रही हूँ, यदि आपको कोई भी डाउट हो किसी भी क्वेश्चन में तो आप कमेंट सेक्शन में मुझसे पूछ सकते हैं. I will be 0.1 ampere. Calculate the work required to turn the coil in an external field, that is given 1.5 Tesla, through 180 degree about an axis perpendicular to the magnetic field. So यहाँ पर हमें the plane of the coil is initially at right angle to the magnetic field, right? Suppose magnetic field is direction में है inside the paper, then the plane of this coil is here. This plane of the coil is perpendicular to this magnetic field, right? So initially theta we can take 0 degree. If current is flowing in this direction, then it will be 0 degree. If it is in opposite direction, then we can take theta is 180 degree, right? So theta is initially 0 degree. And finally, it is saying through 180 degree about an axis perpendicular to the magnetic field. That means finally theta 2 will be 180 degree. So work done will be M is N I A B cos theta 1. Cos theta 1 is 0 degree. So cos 0 degree will be 1. Or next theta 2 is 180 degree. So minus cos 180 degree. So this will be 1 and this will be minus 1. So this becomes 2. So it will be 2 into number of turns are 100. I is given 0.1. Area will be, it's a circular coil, so pi r square. R is given 0.05 and B is given 1.5 Tesla. So calculate this, you will find the work done rotating to this dipole. Now atomic magnetism. So atomic magnetism we know न्यूक्लियस के अराउंड जो इलेक्ट्रॉन्स होते हैं वो रिवॉल्व करते हैं, राइट. सो वी कैन से यदि अगर ये इलेक्ट्रॉन की फ्रीक्वेंसी एफ है तो इसमें हम करंट फाइंड कर सकते हैं. व्हाट विल बी द करंट? I equals to E by T, or we can say E into F. This will be the current. So, and we know omega equals to 2 pi F. So, F will be here omega upon 2 pi. So, this becomes E into omega upon 2 pi, right? And one equation we can write centripetal force mv square upon r equals to k into number of protons. Suppose the number of protons will be equal to atomic number, so Z, and number of proton, one proton पर जो चार्ज होगा वही इलेक्ट्रॉन पर होगा यदि हम साइन पुट नहीं करें, केवल मैग्नीट्यूड की बात करें, into E upon r square. R is the radius. So for this electron if we are calculating, so one equation we have this, and another equation is angular momentum. Angular momentum we have n multiple upon h upon 2 pi, and magnitude of m into v into r. So we have these two equations, and the I we have here. So for magnetic field, how we write magnetic field? Magnetic field will be, for this current carrying loop will be mu naught into I upon 2r, and this becomes mu naught I will be E omega upon 2 pi, 2 it is 4 into r, right? So this will be the B for this electron, right? Now if we write M, so M will be I into A. I will be, we already calculate E omega upon 2 pi, and A will be pi r square. So it becomes E omega r square upon 2. This will be the magnetic dipole of this electron which is revolving around the nucleus. Now we have to add one slide. So here is the सो मैग्नेटिक डाइपोल की इक्वेशन क्या आई थी? E इंटू ओमेगा इंटू आर स्क्वायर अपॉन 2, और वी कैन राइट M इक्वल्स टू E इंटू ओमेगा आर इंटू आर बाई 2, and this becomes E into V into R by 2, or we can write E mvr upon 2m. So magnetic dipole will be E into L upon 2m. L is angular momentum, which we have calculated nh upon 2 pi. So further if we simplify this, then m will be E upon 2m nh upon 2 pi, right? So this will be the equation of magnetic dipole and Bohr magnetron. And Bohr magnetron, that means mu b, is defined for n equals to 1. So it will be m equals to, from here, EH upon 4 pi m. So this is Bohr magnetron. So here we end this chapter. In next chapter we will study about the motion of the charged particle in a uniform magnetic field.